Good day, everyone. My name is Romelin Agbay, and in behalf of my partner, Miss Calunsag, I am going to present to you the actual operation of our assigned topic, which is MOR test, as part of our course learning outcome in CER133.1. So let's first talk about what is modulus of rupture or flexural strength. Flexural strength or modulus of rupture is the amount of force an object can take without breaking or permanently deforming. If this is difficult to get your head around, think about a plank of wood like this one, supported at two ends. If you want to know how strong the wood is, one way to test it would be to push down harder and harder at the center of the plank until it snapped. The maximum pushing force the wood could withstand before breaking is its flexural strength. If another piece of wood was stronger, it would support a greater force before breaking. Flexural strength really tells you the maximum amount of stress the material can take, and it's quoted as force in newtons or pounds force per unit area in meters squared or square inches. The calculation of modulus of rupture is considered crucial in structural mechanics because first, it helps in designing structural elements like beams, cantilevers, shafts, etc. Second, it aids in the study of materials and their properties. Third, it provides a parameter for development of stronger constructional materials. Fourth, flexural strength helps in judging the quality of structures being used for construction. And fifth, it is a tool to predict both resistance and durability of objects. So today I am going to show you the concept behind MOR test. But since we are in the middle of global health crisis, we are in lockdown, and so we are back at our respective homes. So definitely our resources are limited. But as a student of MSU IIT, we should always be flexible and innovative at times like this. As a result, I am going to utilize materials which can be a good representation for MOR test. So these are the materials I have utilized for the actual operation of MOR test. We have a paper and a pen for jotting down the results. We have a measuring scale. We have aluminum rods, 3 aluminum rods. And we have a cement bar, which will act as our sample. So this is a 12 by 1 by 1 centimeter bar in size. And I just want to introduce this DIY machine I have made, but this does not properly work because if you put pressure in here, it still sways a lot even if you have pliers there. And so I have resorted to using just this materials. So let's first measure the dimensions of our sample specimen. Let's measure its length, its width, and its depth. And you jot it down here. So it's 12 centimeter in length. It's 1 centimeter in width. And 1 centimeter in depth. Now we will put markings, 2 on this side and 1 in the center, where we place the aluminum rods, 3 aluminum rods. This is so on these markings, we will put our aluminum rod. So that's it. So what you just saw is a 3-point bending strength test where a continually increasing load is applied in the center of the sample until there is a break or a permanent bend in the material. A flexural test machine can apply increasing amounts of force and precisely record the amount of force at the point of breaking. But since we don't have that kind of machine, as we are limited with our resources, our gathered data may or may not be precise. But anyway, the purpose of this video is to show you the concept behind MOR tests. For a 3-point test, the flexural strength given the symbol sigma can be calculated using the equation shown. This might look scary at first, but once you know what each symbol means, it's quite a simple equation to use. F means the maximum force applied, L is the length of the sample, W is the width of the sample, and D is the depth of the sample. So to calculate the flexural strength, multiply the force by the length of the sample and then multiply this by 3. Then multiply the depth of the sample by itself, multiply the result by the width of the sample, and then multiply this by 2. Finally, divide the first result by the second. Now let's get the results for our actual operation. We have here the given. The maximum force applied is 0.25 kilogram, which is 2.45 in Newton. The length of the sample is 12 centimeter, which is 0.12 in meter, and our width and depth of the sample is 1 centimeter, which is 0.01 in meter. So we use now the 3-point test formula, and we plug in those given. And so we get 441,000 pascals or 0.441 megapascals. So this is the maximum amount of stress our sample specimen can take. Thank you for watching. We hope you learn a thing or two about MOR tests.